This is the CETCO and AST environmental presentation on the installation of FLUORO-SORB Adsorbent for PFAS via injection. So this will be installation in situ for permeable reactive barriers, source area treatment. We're going to get into the technology first, then we're going to talk about installation. But I did want to start real quick by thanking you for joining us today. I also wanted to explain kind of the agreement here between CETCO and AST because we are both individual entities here. Recently here in 2023, AST signed a preferred installer integration agreement with CETCO. So this pertains solely to the injection of their FLUORO-SORB adsorbent material. If you were doing solo mixing or other water treatment application, that does not fall within AST's purvey. But if you're doing work in situ, and we're talking about installing the FLUORO-SORB via injection, that's something where CETCO and AST would be collaborating with you on to come up with a design and installation. And so if you're working with this group domestically here in the US, that would be with AST, but I also wanted to call out, there's probably a number of you internationally here on this webinar as well, and we wanted to acknowledge our international partners, Vertex in Canada, ELSCOF in Europe, and Legion in Australia and Oceania. And so if you are attending this webinar and you see something that's applicable to a current or future project of yours, we do have the network to assist you with that. And so Matt, I'm going to turn it over to you if you want to kick us off with the technology, and then I'll follow Matt with the installation specifications and design.
Sure. Thank you, Derek. Welcome, everyone. Thanks for taking time out of your busy day. As Derek said, we've entered into an agreement with AST and their affiliates as our exclusive injection contractor, and we're very much excited about where we think this can go. We think it makes sense because some of the people on the call may not have heard of FLUORO-SORB. So my section of the presentation is just talking about the technology. And as Derek said, I'll turn it over to him to talk about the equipment and the process of injecting. Just as a brief aside, CETCO started developing this product, I guess, about 8 years ago now. And we initially focused on ex situ filtration in the drinking water market because that seemed to be what was going to be the largest market. We quickly were pulled into in situ work and immediately asked by lots and lots of customers, can you inject it? And our answer was always, we don't know, we haven't tried. As you will see when Derek gets to his portion, we have tried, we can do it, and that's why we're excited to move forward. So, but let's first talk about the product itself, which is FLUORO-SORB Adsorbent. I think it makes sense to just give a very brief background to the company in case any of you on this call are not familiar with CETCO. CETCO's parent company is a company called Minerals Technology, Inc., a minerals mining company. We are just over $2 billion in revenue, just under 4,000 employees, and publicly traded on the New York Stock Exchange. That information about the fact that we're a minerals mining company is germane, as you'll see, to the product. So I will press on. Here's what I hope to talk about in my section. Really focus on an introduction to FLUORO-SORB Adsorbent, tell you how it's manufactured, where it is, and other relevant information about the product. Then we're going to talk about some university work that was done, and it was for water treatment, but again, it relates to what we're talking about here today because PRBs and in situ stabilization, the mechanism is also via water for the absorption, and we'll talk about that absorption mechanism. We'll also go over some of the in situ work we did at the universities, in particular with the University of Texas at Austin. I'll go over a case study for a full-scale in situ stabilization in Canada that was completed last year, and then I'll turn it over to Derek, and he'll talk about the equipment and deployment technology. Then hopefully we have time for summary and questions. Just as a note, if you could put your questions into the chat, hopefully we'll have time at the end, and Derek and I will go over those questions and answer them to the best of our ability. So what is FLUORO-SORB? As I mentioned just a moment ago, the parent company of CETCO is a minerals mining company, and as such, they own a significant portion to the mineral rights for the bentonite that's in the Black Hills of Wyoming, a very particular variety of bentonite. What you're looking at here is the current grain sizes we make of FLUORO-SORB. So what happens is CETCO and its predecessors for over 80 years have been mining that bentonite and turning it into all manner of finished goods. Think of kitty litter, wine filtration, medical uses. Well, the CETCO group has had access to that very same bentonite, and it's been mined and turned into finished goods for environmental remediation. So think of organoclay MRM. And so what FLUORO-SORB is simply the latest modification developed by our R&D group to our base clay, only this time the modification was specifically designed for the adsorption of PFAS molecules. So you're looking at the FLUORO-SORB 100, 200, 300, and 400, the grain sizes we currently make. And if you take a look at these columns, the 100, which is our semi-powdered version of the product, we listed a lot of physical properties here, but I would call your attention to the applications at the bottom. So the FLUORO-SORB 100, our semi-powdered version, is being used for in situ stabilization and solidification, and also in diffusive air filtration treatment systems to replace powdered activated carbon. FLUORO-SORB 200 is the next grain size up. Again, we list physical properties. It's being used for pump and treat, permeable reactive barriers, and in situ stabilization. I'll skip the 300 for now. It's really not germane to our subject matter today, and simply say that FLUORO-SORB 400 is the largest grain size we currently make. It's being used in pump and treat and PRB applications. Now, not pictured here, but important to our conversation, is a grain size that we call FLUORO-SORB P. It is fully powdered, and the FLUORO-SORB P and the FLUORO-SORB 100 are what we used in our injection trials. And again, Derek will cover that a little bit more when we get to his section. So one of the main features and benefits of the FLUORO-SORB product is its versatility in deployment. So that's what brings us here today. We're talking about the highlighted sections you see on the screen: passive groundwater treatment and a PRB or source zone treatment. But I think it's important to note that this product is also being used in groundwater and drinking water filtration by itself as pre or post treatment. And something that's very unique is that last bullet item here, reactive core mat. That's pictured up here on the right. And what a reactive core mat is two needle punch geotextile fabrics that hold in place a known amount of FLUORO-SORB. So this is being deployed all over North America currently in stormwater remediation projects where you're lining swales. It's also contemplated on several large sediment capping projects. So as we go through the presentation, what I'm hoping to show you here is how this product outperforms other products with higher absorption kinetics, better absorption capacity, and for our topic today, very importantly, less effect from competitive absorption. It is fully commercialized. All the lab and field pilot tests are complete, and it was formally launched as a product in May of 2019. So let's get into that university work I talked about from McGill University up in Quebec. What they did was a groundwater treatment experiment, and what they compared was FLUORO-SORB 200, and they compared it with GAC, hardwood biochar, and ion exchange resin. And we can see that for PFOA, PFOS, and total PFAS, FLUORO-SORB significantly outperformed carbon and hardwood biochar and performed similarly to ion exchange resins. Now, for our topic today, what's important to point out here, and I'll show you in a minute, the lack of impact from co-contaminants. But what we know is in situ, co-contaminants are going to wreak havoc on ion exchange resin and on carbons. And so that's an advantage, and we wanted to get some experimentation around that. And so what we did is we had McGill University spike the samples with the co-contaminants you see listed here to include naturally occurring organic matter at a very high dosing of 100 milligrams per liter. And they also spiked with diesel, 1,4-dioxane, BTEX, and TCE. And except for about a 30% reduction in removal efficiency, in the presence of very high naturally occurring organic matter for PFOA, and for PFOS in that high organic matter experiment, there was an 18% reduction in removal efficiency. But if you look at all of the other co-contaminants, you see that there was virtually no impact on FLUORO-SORB's ability to uptake PFAS. And if I could go back a second, if you take a look at PFOA removal efficiency, not in the presence of co-contaminants, you see that it was at about 89%. Take a look at PFOA removal efficiency in the presence of diesel, this dark gray line. It went up to 96%. Now, we are not implying that us or AST are going to be adding diesel to any of your sites, but what it speaks to is a very unique absorption mechanism that really is a differentiator for the product, and I'll cover that unique absorption mechanism in just a minute. One of the other things we want to show you from the McGill work is the experiment that's summarized here. So, as I mentioned earlier, we've been working with this clay for years and years, and we know that it has an immense amount of surface area, but that doesn't mean very much if you can't take full advantage of the surface area. So what we had McGill University do for us is supersaturate the samples with the PFAS compounds you see listed here, these 4. And simply what we were trying to do is see how much PFAS we could get onto our media. To be fair, these rates I'm going to talk about in just a second are not indicative of what you would see in the field, because we're making a driving force of supersaturation. But again, we wanted to show how much we could get on. So what you see here is we got up to 14 milligrams per gram for PFHXS, all the way up to 31 milligrams per gram for PFOS. So we were able to get a lot of PFAS onto our media. So the conclusions from McGill were that FLUORO-SORB is highly effective in removing PFAS from real-world impacted groundwater, and it's superior to GAC and biochar and comparable to ion exchange resin for most PFAS. And again, importantly, it is proven to be effective in mixed waste groundwater conditions. Okay, so what about that unique absorption mechanism? So if you look at the top here, that's a typical isotherm that we see when we do all of the studies that we've done on FLUORO-SORB thus far. We see that it has this odd-shaped curve and there's an inflection point. Well, we had a theory of why that was, and we've since gone and proved that theory. And these 2 images at the bottom are here to help me explain what is going on and why we're absorbing so much PFAS. So on the left, that's an example of what the FLUORO-SORB platelets look like after we do the modification of our clay. They stack up like a deck of cards, one on top of the other, and they're separated by something called the D spacing, which is kept open by van der Waals and other forces. So again, we know there's a lot of surface area, so much so that if you could take these platelets apart and lay them side to side and end to end, 1 teaspoon of the FLUORO-SORB material will have over a football field of surface area. So what we wanted to show was what was happening. And so what we did is we measured this D spacing prior to the inflection point, and it turned out to be 25 angstroms. Then we allowed more PFAS to enter our system and measured after the inflection point, and it went up to 50 angstroms. Now, when I first heard this, that made me worried, because we are doing some ex situ filtration, and it sounded a little bit like swell. And also, you don't want swell if we're doing any in situ. We don't want to change the hydraulic conductivity of the area we're working. But what was explained to me by the professor, and which I now know, is this is not swell. This is happening on the micro level, from 25 angstroms to 50 angstroms. And now we have full-scale field pump and treat systems where we're not seeing any swell, and we're not seeing swell when we put it in the ground. So the reason I'm emphasizing that is people hear that it's made from a base clay, and everyone thinks of swelling when you think of clay. But after we do the modification to the base clay, it becomes hydrophobic and there's no swell. Okay, so that is just a very brief overview of some of the features and absorption capacity of the product. As I mentioned, we wanted to look and see how we would do for in situ work. And to do that, we went to the University of Texas at Austin. But before I take you to their results, I have to take you back to Australia, which is the first place where FLUORO-SORB was tested for in situ work. This experiment that's summarized here was done by a man named Peter Storch, who was working for Arcadis at the time, and Arcadis had a contract with the Australian DoD, who back then and even now is very much interested in doing stabilization, obviously to see if they could avoid building large pump and treat systems. So what they did is they gave some Australian DoD soil to Mr. Storch, and he did various experiments. The control that he did was just to leach the soil with no treatment. And we see that that leached at 228 ppm, so some significantly contaminated soil. His second control was adding cement alone. And one of the reasons he did this is he wanted to establish what it would look like in a high unconfined compressive strength parameter. So he added cement by itself, leaching dropped to 1.17. He also went out and got two commercially available fixins, the first being an aluminum hydroxide carbon blend, which he added in by itself. We see that leaching dropped to 0.75 ppm. And then an aluminum hydroxide carbon blend, this time with the cement, and leaching went up to 245 ppm. So in this case, it leached higher than the control with no treatment alone. And this is likely due to the increase in pH that happens while adding the Portland cement. He moved on and started testing FLUORO-SORB, the FLUORO-SORB product. FLUORO-SORB by itself brought leaching down to 0.30. And lastly, FLUORO-SORB with cement, leaching dropped all the way to 0.04, proving that the FLUORO-SORB and cement was the best admixture. But probably equally as important is proving that the cement did not have a deleterious effect on FLUORO-SORB's ability to uptake PFAS. So he shared this information with his US colleagues who repeated this experimentation and then came up with an admixture of 5% FLUORO-SORB and 10% Portland cement for a pilot at a US DoD site. They purchased 40,000 pounds of FLUORO-SORB and installed this pilot in 2018. Now, what's interesting is at the time, CETCO did not have any data behind this summary that you see. And the reason for that is what Arcadis wanted to do was go back to this site every quarter for 3 years, take a core and make sure that the leaching wasn't ticking up. They did that and it wasn't ticking up. But while we were waiting, we wanted to get our own data, and that's what took us to the University of Texas at Austin. We sent them some DoD soil from a US DoD site. Because it was US DoD and it was a few years back, the action level was the health advisory level of 70 ppt. They analyzed that soil, and you can see that there were several compounds above that action level. So now we skip to the very last slide in the UT's professor's presentation. Now, generally, it's quite a while between those two slides when you're seeing that presentation because there's a lot of information given about how the product was mixed and how long it cured and et cetera, et cetera. But for our purposes today and with the time that we have, I thought I'd jump to the concluding slide of a University of Texas presentation. And what we're looking at here on the left is the decrease or increasing amount of PFAS in the leachate. And on the bottom from left to right is increasing addition of Portland cement. So let's take a look at that top graph, which is the control where 0 FLUORO-SORB was added. We could see with the addition of 3% to 5% cement, there was a reduction in the amount of PFAS that was leaching out of the soil. However, after 5%, you can see that it begins to creep up. And after 10% addition of cement, it quickly became asymptotic and all the PFAS came rushing out. So the next graph we look at is this yellow graph, which was the low dose FLUORO-SORB. Here, they added 1% FLUORO-SORB. And you can see when they got to 5% cement and 1% FLUORO-SORB, they did have one reading below the action level of 70 ppt. But as they added more cement, it quickly got above that and started leaching more. So what's interesting about this is two things. what this shows is with 5% cement and 1% FLUORO-SORB, at least for the soil in question here, you could get to the action level you wanted with a very low dosing. What we have since found, since doing these experiments, is that in many cases that we're working on now, you don't need a high unconfined compressive strength. So FLUORO-SORB is being mixed in by itself. And we'll show you a case study where that happened in just a minute. So the point is a 1 to 2% FLUORO-SORB dosing in some cases will be very inexpensive and effective. But they pressed on because we know there are sites that want to do some development and have a unconfined compressive strength that you want to reach. So here we look at a 5%, that bottom graph is a 5% dosing of FLUORO-SORB, and the university came up with an optimal blend of 5% FLUORO-SORB and 5% Portland cement. But what's interesting here is once you got to 5% FLUORO-SORB, as you kept adding cement, it never creeped up above the action level. Good news if you're looking at a site that has a very high bar to reach for compressive strength. So University of Texas concluded that all PFAS were reduced to low concentrations for all mixed designs containing FLUORO-SORB. And Portland cement alone was not effective in stabilizing these same constituents. Again, they said optimal blend, 5% cement, 5% FLUORO-SORB. I would contend that the optimal blend will be different for every site because you're going to do a treatability on just about every site. Okay, so let's move into this case study for a 30,000 cubic meter stabilization project that was conducted for a Canadian defense facility in Western Canada. What's very interesting about this job is the RFP that first came out said, please provide pricing for excavation, transportation, and disposal of 70,000 cubic meters of PFAS contaminated soil. So CETCO looked at that bid opportunity and said, okay, we're out. But after the prices came in, an addendum came out that said, we have decided to pick a PFAS level under which we think we can stabilize. So the way they did that is went through a treatability study, and I'll talk about that a little bit here. So it was a former firefighting training area. Again, initially the idea was to dig everything up, send it off for incineration, but then they said, well, let's go do a treatability and see if we could stabilize under a certain PFAS value. And that's what they did. They composited 100 grams of soil and mixed it with FLUORO-SORB, and they also mixed it with other commercially available medias. And here's the results for the FLUORO-SORB. You could they did various doses from 5%, 0.5% all the way up to 5%, and you could see that a 1% FLUORO-SORB and a 2% FLUORO-SORB got reductions of 100% for PFOS for the 2% and 92, et cetera, showing that that's an effective dosing. Here, what we're looking at is the comparison of the FLUORO-SORB product to one of the other commercially available fixins, and the FLUORO-SORB product performed significantly better. And so what happened is a bid spec was written that said to the contractors, you can use 1% FLUORO-SORB or 4% of this other product. And the contractors won who were bidding the 1% FLUORO-SORB. So the treatability was done using the LEAF method, LEAF 1314. And you could see that the summation of it is adding 1 or 2% FLUORO-SORB gave you these results. So the control is no FLUORO-SORB or no treatment added, and the PFAS that leached out was at 73%. The 1% FLUORO-SORB PFAS leached out at just over 6% and 2% at 6.28%. Again, the bid spec was written for 1% FLUORO-SORB, but an interesting development there was after the contractor who won it got the job, they talked with the Canadian authorities and said, this treatability certainly proves that 1% FLUORO-SORB will get the leaching down to where you need it to go. However, from an operational perspective, mixing in 1% of anything with homogeneity is difficult. And so they presented that case to the Canadian DND, and they agreed. And what ultimately got installed in this project was 2% FLUORO-SORB. So this product, as I've mentioned a couple of times, is fully commercialized. It's produced in our ISO 9001 certified plant in the US. Probably not germane to our discussion here today, but I'd be remiss if I didn't tell you that it is NSF certified, so it's ready to go for drinking water. Here is a list, a partial list of the publications related to FLUORO-SORB. You don't have to copy these down because we're recording this presentation and we're going to get it out to everyone so that you can follow up and read these papers if you're so inclined. That one discussion I had with the US DOD site, where they went back and kept taking cores to make sure leaching wasn't going up, that did finally get made into a paper, and that's this paper, this first paper here. It's called ACS Omega. It's very interesting, and it's I would highly recommend that you go read it. But again, the recording will go to everyone, and you can take a look. So with that, I would like to turn it back over to Derek, and thank you again, everyone, for your time. All right, not sure if we're having technical difficulties.
Nope, I'm here just firing up the presentation.
Excellent.
All right, is my application slide up, Matt?
It is.
Excellent. All right, so taking over from Matt, this is Derek Pizarro. I'm a senior geologist with AST Environmental. As Matt mentioned, you know, the reason we're all gathered together today on this webinar is to talk about installation via injection. This is a slurry. So if you've seen some previous slides from Matt, some of these descriptions, what we're looking at here is a true slurry of FLUORO-SORB that we're installing in the subsurface. And kind of the background here between AST and CETCO is we've been talking about looking for a new way to install this product, you know, in addition to organoclay and some other products they manufacture. And there were a lot of questions in the industry. How do you install something like this? You know, as Matt said, there's a perception that it's a clay, it's a swelling clay. As he mentioned, that's not exactly what's going on here. But at the end of the day, it does end up being a true slurry. And if you're not familiar with AST, our background, you know, our primary competency is injection of slurries in the subsurface. So when we first got to this discussion with Matt and CETCO, we said this is doable, but we need to do some bench evaluation. We want to do a field demonstration, things that you would naturally do anyway. But we're able to lean on more than 15 years of experience with slurry injection. And by that, I mean the way that we install the FLUORO-SORB and other slurries is with water and energy, right? We're suspending it in a mixed tank with just water as our carrier fluid and energy. So this isn't, you know, an addition of guar or other suspension reagents, additives, things like that. So this is a very natural fit for AST. And as you see on the slide in front of you, there's a lot of different ways to install this product. Matt mentioned some soil mixing or trenching. That's a little outside our purvey here for the injections, but in terms of overburden, bedrock transition zone, competent bedrock, we found that this product fit almost exactly with a lot of the installations we were already doing. So our top-down direct push installation with slurries, very familiar to those of you who've worked with us before. Same with the pre-drill technique, which we call geotap now. That's to access transition zones, saprolite, glacial till, cobble zones, things like that. And then obviously bedrock would be straddle packer injection. So we found the product and the design very similar to these geologic settings that we're already dealing with day in and day out at AST. So I'm going to focus on overburden because two notes, I think overburden and PRBs are the immediately actionable installations with this product, be it for a pilot, a demonstration project, an IRM measure, certainly full scale is part of that as well. But I think that kind of approach is where we can build into a portfolio here of injectable FLUORO-SORB. And so if I focus on overburden, when we do slurry installations with FLUORO-SORB here, we're talking about top-down injection, right? Offset vertically, offset triangular grids horizontally or laterally, right? We're trying to create this complete interleaving pattern throughout the subsurface. And because this is a true slurry, we're not driving down to the bottom of our injection interval and working our way back out. That doesn't work well with slurries at all. So we do this all top down. In terms of some of the design, again, this does lean on our experience with slurry injections. Designs for slurry injection, depth is a major component of it. The type of geology you're injecting in is a big part of it. The slurry loadings, right, which, as Matt mentioned, we would get through bench testing and evaluation. As it stands right now, we would take those loadings from your discussions with CETCO and apply those to a design pattern that we already use for slurries in the field, and make some optimization and adjustments to that both during the design process and then immediately when we start in the field as well. And then the last thing, I include tip geometry on this installation slide because we make our own injection tips in-house from GeoPro blanks. That design, again, is primarily predicated on geology, but depth and some of these other considerations come into play as well. So what does a slurry look like in a fine grained or a coarse grained installation? We have those two examples here set on this slide. The one difference is I would note with the injection in fine grained materials on the left, this isn't just a uniquely linear feature, right, in the subsurface. They're not exactly planar. At the pressures that we inject at, we actually get propagation into the clay patterns, the interstitial platy mineral networks that exist within them. And so that's what we're looking at here in this core. As you can see that this picture here in both cross section and plane view is that this isn't immediately within the injection interval, right? So this is the distribution into the finer networks away from the injection swath that we started the injection. Certainly there is that fracture or linear feature, but this just goes to show you that there's some additional tertiary propagation away from those injection intervals that isn't realized under low pressure injections, which you wouldn't use for a slurry anyway. And then on the right over here, the installation swath right here, we have a darker material in a medium to light brown. And you can see that here in a coarser material, we're radially co-mixing. So we're actually increasing the injection flow rates and pressures because we want to tumble, so to speak, the material that we're injecting, the FLUORO-SORB that we're injecting with the formation around it to create contact. If we didn't make those increases in the energy, we would see formational straining regardless of the type of slurry, if you're dealing with a true slurry that you're installing in the subsurface. So I just want to go back. The one thing that is a little different with a slurry than maybe your traditional injectates that are liquid aqueous colloidal is that we typically inject on much tighter grid spacing. And that's not to say that this setup takes much longer to install or it's more expensive to install. In a lot of cases, they're about the same time or less than a traditional ISCO or SCUR application. And that's mainly because we're not limited on pumping time, right? Our pumps are cycling every time we shoot an interval for 15, 20, 30 seconds, typically at a time. And then we move on to the next interval. So when we do these tight spacing triangular grid patterns, again, predicated on geology and depth and the shot volume, we're not hung up out there for days, right? If we can make a lot of probing production in a day, we can get a lot of material installed in the ground. So this tight spacing also allows us to control where the material is going instead of just pumping and connecting up with preferential pathways, utilities, other things in the subsurface that would create a change in injectate direction, which we don't want in most cases. Again, I think a PRB is immediately actionable. Trenching it, right? If you have a trenchable application, certainly reach out to Matt. If you can do these with yellow iron, you probably should. There's a gray area there. There's some applications where maybe both could possibly be effective, but generally yellow iron versus injection, it's not hard to differentiate which one's better. If you are doing injection of FLUORO-SORB, you're looking at, leaning on our expertise with PRB design here in this example. One of the things I will note is, and we get questions, not just with FLUORO-SORB, but other slurries as well. Does this work as well as a yellow iron or heavy equipment installed PRB? And the answer is, if you do your homework up front, absolutely. And so in the example I'm using here, this is just a grid design I pulled from another site where we installed a slurry. We're trying to tie it up. You can see the creek here. that we're trying to protect as our sensitive receptor. In here, based upon mass flux and the geology, we elected for 4 unique rows or curtains in this PRB. I would say typically PRBs are 3 or 4 rows. In some extreme cases with an immediate adjacent continuous source, you might find a 5th row or a modified 5th row. But injectable PRBs are certainly a modern application for this slurry. And so I'll close with, before we open up to questions, again, if you do have questions, please use the question and answer box or the chat. These pictures here are for a demonstration we did last September. This was solely to prove the installation techniques, designs that we typically use are compatible with the FLUORO-SORB. We know when the loadings are correct and the distribution is effectively designed and competent, that we will get contact and thus remediation here. And what we're looking at here on the left is, again, our DPT approach. This is a slurry rod cart, right? So we can continuously inject as we move down. This pre-strung hose goes through the injection rods, and we can continue top-down injections in rapid order with a very simple geoprobe or AMS rig. We did this demonstration with our skid system, so this looks a little bit different to some of you who have worked with us than our trailers, but this allows a nice view of our double pump system with a mixed tank. We got water tank here, and this would be a fairly typical setup for a slurry, right? Using the recirculating pump for the tank, and then the double pump system for the injections down through the pre-strung rods. Here's what the FLUORO-SORB looked like in the mixed tank. This first one here is FLUORO-SORB 100. We piloted both FLUORO-SORB 100 and FLUORO-SORB P. P, think it is powderized, it's powder or micronized. But here we're demonstrating, this is as we're building our 1-to-1, and 1-to-1 being 1 pound of FLUORO-SORB to 1 gallon of water. We did test multiple loadings up to 3 pounds per gallon. But here we are building that first mixed tank, and you can see from a dipstick here, we pulled some out and poured it into our hand. You could see that we do have true slurry in this mixed tank. There are percent solids, and they are, in this case, a significantly larger surface area than most of you are used to for, say, something liquid, colloidal in your installations. I pulled this picture with the dip cup here from the demonstration to show you that we are only using water and FLUORO-SORB. You can see here a minute after this has been pulled out of the tank, the product does start to settle. So we are truly suspending this with energy within the mixed tank and then flipping a valve and then shooting it directly into the subsurface. So I'm also going to point out here that what we see here, this is not fluff, this is just settling. So here's our basal layer. Here's this kind of unsettled, yet to fall out a solution layer, and then some of the fines associated with it. So I'm going to go back to the example Matt used, because again, I just wanted to reiterate that we think a permeable reactive barrier, whether it's just solely for PFAS, whether it's PFAS and CVOCs or another contaminant, we think these are immediately actionable today. I would say right now we're working with a couple of clients where they do have a mixed PFAS and other contaminant plume. We are looking at how to sequentially stage some of those injections, right? Like, do we want the FLUORO-SORB to be a precursor to the other treatment mechanism or vice versa? Right now, most cases we're tilting towards the FLUORO-SORB as the precursor here, as you can see in this cartridge setup that Matt discussed, but that could change. We're also working with a couple vendors to look at co-mixing the FLUORO-SORB with other reactants and amendments to have them co-injected in one event for some applications. And here's a little bit, just a closer dive on that cartridge here with the FLUORO-SORB, the gabion baskets, GAC, and the engineered soil. And so I'll close with this, and this case study is available through Matt or AST and some of our affiliates. But what we're looking at here is our upgrading influent, the measurement within the cartridge or reactive zone itself, and then what we find in the discharge and down gradient zone. And what we've supposed from this here is the immediately proximal discharge zone here. This is actually bleed back from the down gradient zone. We expect this number as time persists and we've cut off the source, right, so to speak. We expect both these numbers to decrease significantly. But we are showing that within this reactive zone, we are getting capture of the PFAS. All right, in the interest of time, I'll open this up to questions. Matt, if you want to come back off mute here.
Yeah, am I off mute? I am. I see the Q&A section, it looks like there's 8 questions, and we could just pick them off one by one. If some, I'll read them, Derek, and if it's in your realm, you take it, and I'll take it if not. So the first
Absolutely.
question from Greta is, have you seen high iron in groundwater affect efficiency? We haven't seen that yet. We haven't done a full-scale pilot in the field for injection. What I can tell you about that, though, is one of the first projects we were on, a landfill operator wanted to pump untreated landfill leachate through FLUORO-SORB, and it had high iron, high manganese, high everything. And we did see armoring of the media. We still had flow, pressure went up, but we still had flow. And what was interesting on that project is the lead vessel acted like a sacrificial lamb. So the iron fouled it and biological growth started. And like I said, pressure went up, but it still flowed, and it went through the lag vessel, and we're meeting the discharge criterion. So if there's a lot of iron, what we would need to get from you is the expected groundwater flux and the concentration of iron, and we can look at it based on our existing data. I hope that helped. The next question is from Dan. In your leaching and sorption test, have you analyzed the leachate with AOF, EOF, top assay, or some other method to quantify non-targeted PFAS? So the leachate that comes out of the leaf method, it was sent to a third-party certified lab. I believe they use top assay, but I will get additional information for you and send it out. The next is from Anonymous. Is there a minimum source area size, impacted depth, minimum or maximum, or minimum PFAS contamination level you would recommend before considering the use of FLUORO-SORB? Derek, I'll let you talk about minimum size and depth, but as far as minimum PFAS concentration, if you've got a sensitive receptor that some regulatory or other target has been set up for, then there is, and you think that the concentration, the existing concentration is so low that you're not going to hit that, go over that target value, then we wouldn't recommend FLUORO-SORB. But, you know, as we know, when you're talking potentially 4 parts per trillion, I think most PFAS contamination would call for some form of treatment. And I don't think there's a size that or depth that we would have a problem. Well, I shouldn't. Derek, why don't you talk about that?
Yeah, I'll jump in there. So there's a couple questions here about size, whether it's source area or PRB, depth, slurry injection loadings. There's a question about this deployment in bedrock. I'll try to wrap those all together here in one answer. In terms of size, no, really the only restriction in size for this deployment, whether it's small or large, is what makes practical sense from a protecting a sensitive receptor, human health, cost or budget, right? That's obviously a big player. We've installed slurries and postage stamp 150 square foot areas before. We've done expanses on the tens of thousands of square feet before. So really we would work with you to make sure that the installation matches your goals and objectives. There would probably be some decision-making that goes on to determine, what is most critical. If there is a cost and budget factor that's going to significantly constrain the ability for us to meet your criteria, we would discuss that with you up front. In terms of the loading, and this would apply to overburn, transition zone, or bedrock, the loading will be predetermined, working primarily with CETCO. There would be some input from AST, but once we have that loading, say on a pounds per cubic foot basis, that's where AST and our affiliates' expertise in slurry installation and design, design and installation comes into play, and we back into what that design looks like, taking into account depth and geology. As far as the bedrock goes, this is deployable in bedrock as well. We find that this product, from a compatibility standpoint, fits really well with some of the other injectates we typically work with, say like activated carbon and some others. So if we did look at working with you on a bedrock site, it would be more of a traditional bedrock investigation, getting loadings to SETCO so we can back into loadings that we can install on the fracture network and the subsurface. Let me see, was there another one here on that? In situ spacing. So the spacing of a grid for a source area, or the spacing for a PRB, both row adjacent or between rows. This again would go back to depth and geology. I would say as an overarching comment, depth is probably the most important factor in what we're doing. Like, it's going to be very hard to install if you want to put a PRB just a foot or two below the subsurface and terminate, say, at 8-10 feet. That's a very tight grid pattern. But as you start to step out with these installations, you get below 20 feet, especially, you start to get onto DPT style injection centers that could be 7.5, 10, maybe 12 or even 15 feet, depending on the application. So again, the depth plays a lot into this, the geology, right? What are we doing? Fine grain material or coarse grain material, that plays into this as well. Yeah, go ahead.
Yeah, just two questions came in above where we were working, so because I went back up and checked. The first one is, are the leach tests just a snapshot in time, or do they somehow predict how long the PFAS will stay sorbed? Well, that's a very good question. The leach tests that we have had run on the various jobs that we're on are either the leaf method, semi-dynamic leaching leaf method, or SPLP. And we've had many discussions about that. The regulated community is going to have to decide whether those testing methods are sufficient to establish risk. And so that's everybody that's working with this is either SPLP or the leaf method. What we could tell you for sure is I went over that adsorption mechanism, showing you how the galleries open and PFAS gets into those galleries. We know our bond is strong, and we know that once inside the galleries, it's a tortuous path to get out. As far as empirical data, if you look at that paper by Arcadis, they went back for 3 years and saw no increase in leaching. So empirically, we've got data saying that 3 years is very doable. With respect to how long it would last overall, if the regulated community decides that the SPLP method or the leaf method are sufficient, because they have built in stressors that mimic time. So that's where it kind of where it's headed with leachate testing.
You want to just quickly hit on, there's a couple about ex situ treatment here, and that's something they can reach out to you for after the presentation.
Yeah, and well, here's the top, absolutely. And I think if we don't, their questions keep coming in. If we don't get to all of them, we will go in and write out answers and get them to you. But the latest one that came in, it says, for co-contaminants test, does FLUORO-SORB adsorb any other common organic contaminants such as SVOCs, BTECs, etc.? So the answer to that is FLUORO-SORB is showing fantastic adsorption capacity for PFAS, but it will also absorb organics inversely proportional to their solubility. So for instance, in BTECs, it'll have about, for benzene, which is fairly soluble, it'll absorb at a rate of about 20%. For PCBs, it'll absorb at a much higher level. So again, if it's highly insoluble, the FLUORO-SORB is also going to absorb that. 1,4-dioxane, for instance, very soluble, will go right through it. So I hope that answers that one. Do you see any that we missed, Derek?
I was looking at the vadose zone, saturated zone.
Yeah, yeah, that's funny. We just talked about that.
In AST's experience, we're typically treating just the saturated zone. I don't know about the unsaturated zone applications, Matt. Usually with a lot of the reactants that we install, vapor transport's not the most efficient use. In this case, not even really applicable. So I don't know what you'd be doing there. Maybe the soil mixing that you mentioned at the outset of your presentation.
Yeah, I would picture if you were across a smear zone, or if you were, all in the saturated zone, then clearly that we can inject and get propagation and get it treated. But if you're also contaminated in the vadose zone, maybe we look at a traditional soil mixing on top of the injections.
There's a question for you, Matt. Does CETCO offer bench treatability testing and/or column studies for design support?
We do, but the bandwidth is making it take a long time, because there's been so many requests for it. So what we've done is team up with some other providers, and we can give all the technical support about how to set up the columns, whether you go RSSCTs or, all of the technical stuff will help with that. But the actual doing of the work, we may point you towards one of our partner suppliers.
Question about particle size. FLUORO-SORB 100, FLUORO-SORB P.
Yeah, I don't know that off the top of my head, but we have the D50 and all of that data. So I think that's from Elliot. I will make sure I get an email out to Elliot with our sheet on sizing.
Okay. All right, I think last question here. Well, actually, there's two here. One just came in as well. So let's go back to the first one. What is the expected flow or flux through a cartridge as shown on the PRB example? Is there an expected hydraulic conductivity?
So both the 100 and the P are 10 to the -3. In these situations, though, we're injecting into whatever the hydraulic gradient is of the substrate, and so it would be a blend. Generally speaking, we don't want to be less porous than what we're injecting into, and for most of the projects that we're in the process of going at, look, we have a few certed projects coming up. In most of them, the 10 to the -3 was appropriate or sufficient.
Okay, last question here before we close. How long would you expect this treatment to be effective? Would you need to dig it out or inject more? That kind of depends on the application. We did show the cartridge application there in the PRB example from Canada. I would envision that would be monitored and could be swapped out. And that may be the impetus for some of their design, whether it's just a funnel gate application like that, whether it's trenched, whether it's injected, you can make some of those assertions. It's really very project specific. I think one of the things that we're looking at as collaborators here within CETCO, AST, and our affiliates is really looking at installing for a lot of these, especially, again, going back to that PRB application, because I think that's immediately usable and viable for our clients and attendees here today. That PRB application there is, as a lot of deployments are right now that are considering something like activated carbon, it's a very similar setup, right? Except that here with the FLUORO-SORB, we know from the testing that, Matt showed some of it. There's also some more he has on tap as well that you can reach out to him for. But we know that the capture, the capacity, the longevity of those installations, obviously situation dependent, are more robust than a scalable application of activated carbon. IX, not usable in situ, probably ever. It's definitely not injectable right now, as far as any of us know. He had some examples there with biochar, activated carbon. Again, those don't have the same capacity as the FLUORO-SORB, as you saw in some of those demonstrations. So I think our immediate deployment here in a PRB application is to protect a sensitive receptor, a property boundary line, and then there's a monitoring period that's going to be, and program that's going to go along with that. And it could be something as simple in the design process as accounting for possibly at some point, years down the road, decades down the road, adding additional rows of installation points. I don't think we would remove it right now. A lot of these installations that we're seeing proposed are effectively managing this in situ until another remedy comes around that is usable. So I don't know if there's anything you want to add to that, Matt, but I think
I do, because as you can imagine, this question comes up fairly frequently, and I think the best way to answer it is sort of anecdotally. And what I mean by that is we are working on a traditional PRB on a Superfund site. And the request from the engineer was give us the dosing of FLUORO-SORB that needs to go in to get 20 years below the detection limit. And in this case, it was just PFOS and PFOA. So what we asked them for was the information on all of the water quality, the flux. This, by the way, this PRB is going between a body of water and an unlined landfill. So it has other things in it. So all we needed from them was give us the concentration of all the PFAS, not just the two that we're going after, and all of the other water quality data. We got that data. We have a very extensive model after 8 years of pilots and lab studies, et cetera. And we have absorption capacities for at least 40 different PFAS. So we plugged that into our model and we reported back to the engineer that in this case, a 6% by weight dosing of FLUORO-SORB will give you 40 years below the detection limits for the two PFAS that they requested us treat for. So that answer came from us crunching our model, and we could do that for any given situation. On that particular project, they came back and they said, that's great. Now add these 4 or 5 PFAS to be below detection, and how long will it last, and we're crunching those numbers now. So it's an iterative process where you give us the data and we put it into our model, and we can come up with a dosing for you.
Okay, well, it looks like unless anybody has a last second question to file for me or Matt, it looks like we are concluded for today. I appreciate everybody taking time out to sit with us on this webinar, spend some time. I realized here, and I apologize, we don't have our contact information on this final slide, but we're not too hard to track down, both on our respective companies' websites and LinkedIn. So if you need our contact information, it's on there. Matt, you want to plug your website real quick?
www.cetco.com. And I'm putting my email in the chat now.
Yep. I'll put mine in there as well. We are ASTENV.com. And we appreciate everyone's time. Feel free to reach out to us with questions offline. And if you have colleagues who weren't able to attend today, we have a webinar tomorrow, 8 a.m. Eastern. That's primarily for our European clients. And then also Thursday as well. That'll be at 3 p.m. Eastern, 12 West Coast. That'll wrap up our webinar series here on FLUORO-SORB and injection. So thank you for your time, and everybody have a great week.
Thank you.